what are the relationships among these diols? Well, we can pick out two mirror images of each other. An easy way to draw the mirror image of a compound is just to take all the wedges and make them dashes, and all the dashes and make them wedges. So if I do that, which is called configuration, so if I change the configuration at all the centers, then that is essentially the same as drawing the mirror image. And so those are enantiomers. Again, I can't sort of rotate them to look the same. So I've got two sets of enantiomers, two pairs of enantiomers. But what are the other relationships? Again, they have the same atoms and the same connectivity, right? They're both carbon chains with two OHs, on carbons 2 and 3. They're both 2,3 diols. So what's that relationship? Well, we can say that they have the same connectivity, but they've got different shapes. Again, I can't take any of those four and kind of manipulate it or twist it or squeeze it to make it look like any of the other four. So we're going to call the other relationship diastereomers. So diastereomers have the same connectivity but different shapes. They're not mirror images of each other. Okay, so we've got two sets of enantiomers, and then the other relationships are diastereomers. Let's try this again. We've looked at cis and trans substituted cycloalkanes before when we talked about naming stuff. So what are the relationships here? Well, in this case, again, it looks like we've got two sets of enantiomers, but we actually don't. So we have one set of enantiomers, and if I redraw those, you can kind of see how they are different. In a way, one is kind of like a left-handed screw and one's a right-handed screw. But the other ones actually are the same molecule. So if I've got sort of two things with two pointing up and I just flip it over, now they're both pointing down. So here I'm just flipping those two. So those two are the same molecule. And so that's kind of weird because we can look at those carbons with the wedges and dashes on them and say those are chiral centers. So if I look at the four substituents on those carbons, none of those four substituents on each carbon is the same. But those are chiral centers. So how can I have a molecule with two chiral centers still be achiral? Well, this compound is called a meso compound. It's got a plane of symmetry, a mirror plane, that reflects the one stereocenter into the other stereocenter, or chiral center into chiral center. Okay. So because those chiral centers are reflected into each other, the molecule is not chiral. Its mirror image is just the same as it. So one reason I point this out is because to show that diastereomers don't need to be chiral. Right? So the molecules on the left are both chiral. They are enantiomers of each other. And they are diastereomers, each of them, with the molecules on the right. The molecule, I should say molecule on the right, because those two are the same molecule. So something doesn't need to be chiral in order to have a diastereomer. So to recap, most of the time when I see a chiral center, a carbon with four different things on it, I know that that compound is chiral. It's not superimposable on its mirror image. I just showed you cases where I have chiral centers, but the molecule is still achiral because it's meso. There's a mirror plane in the system. But it also goes the other way. There are a few compounds that do not have a chiral center, but are still chiral. So how should I think about that? Well, it comes back to, is it superimposable on its mirror image? So here you see something called binol. So binol, again, is all sp2 carbons, but it's stuck in a helical shape. And it can't really rotate back and forth easily. So this compound is different than this compound. Again, it's like a righty-tighty screw versus a lefty-tighty screw. Right? And so I can actually separate those out, and those are enantiomers of each other.